Hey y'all, I'm here for the second part of homework 5. This will be the last video for homework processing dynamics and controls. Hooray. We will now start with the first part, which we will derive algebraic amplitude ratio and phase lag of a proportional integral controller. So it's different from our usual proportional controller. We are now being using integral for the controller. When we do, we'll be using a proportional integral controller, so it'll be something a little bit more different, adding on to our normal controller. For this, we're explaining why a first order system with a PI controller will always be stable, whereas second order, first order with a time delay, would not be stable for some controller parameters. Okay. So the first part we would derive, using my iPad. And hold on, let me. Stop video. Sorry. Something looked off on my screen. So first we will derive the PI proportional integral controller on iPad. Then the second part we will go on Python and explain why the PI controller will always be stable compared to the time delay, which I kind of answered the second part in the part A when we coded out the time delay and also derive the time delay as well. But we can just restate that. And then for the second part, we will do the FOPTD, which is just uh a model using the PI and the time and a combined time delay model with it, and then using the parameters that we have set, and then we need to make a plot. Okay, so let's start with the derivation first. So let me switch my screens. Let me I always forget to do this, so bear with me. Share software screen. There you go. There you go. Start broadcast. Oh no. Start broadcast. Okay. Do, 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 do. So we will start with a closed loop system, like we usually do. So for our closed loop system, we have our set point going in. We would say this is just YSP because we don't have a determined parameter or a desired parameter we're trying to change. So we just do YSP. We know it goes to the calibrator. I'm pretty sure that's what it's called, a calibrator, or yeah, calibrator, which shoots us out an error. Error, which shoots out the error. From the error, we can then get our controller. So RGC, which is just RKC, representing our KC in this case. From our controller, we can then shoot out we can put in a certain condition for our process that we want. That goes into our process, our initial state for our process, where this is represented as U. This then goes to our GP, which is our process. And then let me zoom out a little bit, which is our process. And then we go here, remove this as well. Oh no, we need to go to the bottom. Um, which then at the end it shoots us out an output, which is our desired results. Well, it just shoots us out our output from the controller. Okay. We know then this also goes to a measurement device system, so our GM. So from our output, it goes loose back to a measuring device system, which then shoots back to the calibrator. We know why it goes into the measuring device system because we need our output for the measuring device to measure or to measure something. We know our measuring device is also one, and when I forgot to also mention that our process, we know it is K of tau S plus one. Okay. The next, from our measuring device, we get Y times GM, which then goes into the calibrator. So then we have Y we have the set point, uh, plus our Y times the measuring device, which shoots us out our error. Okay. Well, plus our measuring device shoots us out an error. But yeah. This is our closed loop system. Same as we always use it. Same thing. But we do have to We know since we're using a proportional an integral controller, our controller KC will be different in this case. Okay, so we have to account for that, and we can actually derive that as well to see what the difference will be. So we know usually for our KC, we just have um we would just have KC times our error, which is just from our system. They match, they go in together to get our um, input into the process. But now we have to also incorporate the other part due to the proportional integral controller, which is Kc times 1 over tau I to the integral of 0 to time of error times the change in tau. Okay. So tau I here, this is a reset time. And what it is basically just the error times a time, a certain time, which will give us actual tau by. But this is very important for the proportional controller. And this will actually help us understand why the proportional integral controller is actually more stable than a regular proportional controller. Okay. So if we do the math here, we know that we get that from the integral, we'll get Kc. Oh my gosh. My writing's atrocious today. Bear with me, please. Kc times the error plus Kc. Why are you not right? Why is it not writing? There you go. Kc times 1 over tau I times epsilon of tau I. Okay. And this part's from the integral. We know the tau i's can cancel out. So we would just end up with Kc times error plus Kc times error. Okay. So this is what our new Kc output would kind of look like. I mean, Kc value would kind of look like. We're not done though. This is, we have to know that this is also in the outside of the Laplace domain. So we have to put this into the Laplace domain. So we next have to, again, like I just said, put this in Laplace. So we have two expressions to put into Laplace. It is this bad boy here and this bad boy here. So we have two functions that we need, two expressions that we need to put into Laplace domain and combine them at the end. Okay, so we can do the first one, um, which is just case Laplace of Kc times the error, which is just Kc to big E. So the error goes to Laplace. So it'll be capital E. Then for the second part, you'll have Laplace of Kc to 1 over tau I of the integral of 0 to the time to the error times a change in tau. Okay. We know that that Kc and the 1 over tau will stay on the outside. Oh, will just stay the same. I mean, and the error will become a capital E. So we have a capital E, same as the top, and then we'll have 1 over S for the tau. Okay. So now we can combine them. So we will get Kc times E plus Kc of 1 over tau I of E over S, which is just equal to, so we can factor out the Kc and the E. So equal to Kc times E of 1 over tau I times S. Okay. So this, and let me actually reposition this because I'll explain it later. Here we go here. So this is our final equation, the final product for the change of the controller for KC. And actually we will just, for this, we will put this as our new KC value. So we'll plug this in back into we'll use this expression for the KC. So instead of just having regular KC, we'll use KC times 1 over tau I plus S. And the reason why we not to use the error because error is already incorporated into our controller. That's one of the main values to get our controller. So we do not have to restate the error since it's the basis of how we form our controller. Okay. So we don't need the error here. Kind of goes away. But we do need a KC of 1 of tau I of S. Okay. So now if we make our overall equation, uh, we know that, our set point, what is it? Well, set point times our closed loop function is equal to our output. Okay. We know our closed loop function is equal to, and that help me out. G, oh my gosh, G, oh my gosh. There you go. GC times GP. So the controller times the process divided by 1 plus GC times GP times GM. Okay. All right. And then if we use all the terms for the respective transfer functions, we know that GC, we can plug in the we have for GC, which is now the new K that we have. So we have KC of 1 over tau of I of S times GP, which we know GP is just 1 over tau of S plus 1. Okay. Divided by 1 plus, and then the same in the bottom, tau by S, and then 1 over tau of S plus 1, and then just 1. Okay. This is our closed loop transfer function. Okay. And what we would do after this, we would do the final product theorem. But I will not do that because that's a lot more time. And it's I can just explain the output of what we get. So from the final transfer the final value theorem, when we get the limiting function, the limiting value in S is equal to 0. We'll get that. We will get 0. We will get 1. Uh, so we know that our controller. So we know that our set point, our output is equal to 1, which is actually amazing. This basically means that what we put is what we oh my gosh, I can't talk. What we put for our set point, we will be able to actually get what we are desired for our set point actually to our output. So since it's 1 to 1, and the final product would be I think KC times K divided by KC times K, and which is this 1. Whatever we set for our set point, our output would actually match. So it'll match our set point. So whatever we want to have for our controller, for our desired set point, we will have for our output, which is much better than what we will have, what we would have if we used just a regular proportional controller. So that's one of the reasons why, well, the biggest reason why the proportional integral controller is way more feasible and more reliable than just the proportional controller. And now we'll kind of explain this furthermore in the time delay. So now we can go to our amplitude ratio and our phase lag. Okay. So I'm gonna choose a different color and I'm gonna use the next page. Let's just use white. So amplitude ratio. Okay. So we know of course, for DCL, not DCL, but our controller. Hold on, I think I messed up actually. Did I? Trying to think. I'm trying to think. Let me check real quick. I think I did mess up. Let me check real quick. Okay. Yeah, I did. So I made a small mistake. Because I knew something wasn't right. Because when I did about to start a neighbor to ratio, I felt like I was missing a term, which I actually was. So for our controller is actually since we factor out the KC in an error, so we factor out the controller in error like we did earlier. We actually is one plus because remember it's two expression is one plus something else. So one plus and then the one over tau s is tau I of s. Okay. So this is actually the correct answer. Okay. And that would actually represent in here as well. So we need to change these. Let me just use a plus one. Let me kind of sneak that in here. All right. Yeah, it's just, I just had to incorporate plus one. So now back to our empty ratio. Um, our controller, our DC is equal to KC time KC of one plus one over tau I of S. That's why I was kind of important. So of course we have to substitute the S for JW, J omega, I mean, which is just KC of one plus one over tau I of J omega. And next, we usually do we'll multiply by the conjugate of the complex number in the denominator. But this time we're actually, what is it called? We will we'll do something. We're not gonna multiply by the conjugate. I forgot what it's called, the algebra term for this. But basically we'll multiply by the negative J. So multiply the numerator and denominator by the negative J. Why is it? I don't know to my tongue. It's relative. I forgot. I forgot. I'm not going. I forgot. I'm not trying to make up nothing. But what we will do, I do know the process. What we will do is that we will multiply. So KC of one plus one over I of JW. So what we'll do is multiply the numerator and denominator of the fraction by our imaginary number, negative JI. And that'll give us negative J of negative J squared of tau I omega. Okay. We know, of course, negative Ji just goes negative Ji squared goes to one. So we have negative one, which then that cancels out the other negative. So and we just have one here. Um, yeah, we just have one. And then we'll factor out the negative J outside of it. So what we will end up with is KC of one plus J of one over tau by omega. Okay. Oh my gosh, omega looks nasty. Again, sorry for the atrocious handwriting. I would try to go back to the library if my handwriting is bad. On the iPad. But from this we can get our real and imaginary numbers. So for our one would be our real term, and then our J of one over tau I omega be our imaginary term. In this case, And then we can now plug this into our empty ratio. So we know that AR is equal to radical R squared plus I squared, which that would just be radical 1 squared plus 1 plus J of 1 over tau I omega squared. Okay. I think we can just I'll actually leave it like that. Um, I think there's no harm in trying to factor everything out. Um, yeah, I think we can leave it like this. Okay. I think if even if we did, I think what we just have is what 1 plus no, because we have to actually do the multiplication of 1 plus. Yeah, we can leave it like this. But that is the correct factor for this. And I'm gonna see if we need to express this further out later. If we do, I'll just record that. But I think we're fine leaving it in this phrase. Next we can do the phase though. So phase, the phase is the inverse tangent of I over R, which then we know that is just inverse tangent of 1 over J of tau I omega divided by 1. That's just that. So we end up with, oh no, I'm sorry. That is, I expressed this wrong. It is, let me refer this out, but it's 1 over J of 1 over tau I omega divided by a big one. Okay. And then we can cancel that out. So then we will just end up with inverse of tangent of, what is it, J 1 over, oh, it's not 1 over anymore, but tau I omega. Hold on real quick. My computer about to die. Okay, I'm back. Sorry about that. My computer is actually on low battery mode right before, and it does not last that long. So I need to hurry up and do that. But I actually got a chance to check, make sure everything was right. A few things. I actually put J into the terms, even though we're using that for imaginary terms. So we don't need J for any of these statements here. I can rewrite this. And also this would be negative. It's kind of just stated here. This will be negative on top, so negative will come down. So it'll be negative here, but it'll be expressed positively here. Just due to the fact that we have squared. Anything squared is positive. So, and then for the negative inverse, the inverse tangent, like I said, we have 1 over tau I s, or tau I omega over 1. That just cancels out. And we will end up with, it will still be 1 over tau I omega. Okay. So this is our phase and our empty ratio for the phase lag and empty ratio for the proportional integral controller. And from this, we can actually state that when omega is very high, so if we have a high omega, we know that anything, so anything very high, so 1 over infinity, we know it just go to 0. So we know omega, if our omega is very high, it'll just go to 0. Our domain. So for our domain, if we have our extremely high omega, we know that that would just be equal to 0 because omega is on the denominator. Now as we increase our denominator, our number will shrink overall. So that would just be go to a zero term. So our omega is zero when our domain is zero when our omega is very high. And then when our omega is very low, so we have like 1 over 0.00001. That'll actually give us to, oh, excuse me, pi over 2. So I guess a 90 degrees, well, negative 90 degrees. Um, okay. So we know that from this, we know that our domain from our PI controller is just from 0 to negative 90 degrees, which means that we will have a stable function throughout um, that we would never reach negative 80 degrees. It's kind of impossible due to how we have yeah, it actually is impossible. Um, if we don't incorporate anything else like a time delay or anything. But just using our proportional integral controller, we would never reach negative 80 degrees, which means our proportional controller will always stay stable. Okay. Which kind of moves on to our next part of just kind of explaining why the proportional integral controller um will be stable compared to the first order or second order time delay proportional controller. Okay. So let's move over to Python and we can explain that. Okay. Hey y'all. I'm back again. This is what the last part of part B on the Python version. I don't believe there's any more derivation parts. Let me there we go. I don't think there's any more derivations that we have to do, so everything else will be with Python. So let's wrap up the first part of part B, where we have to just plot out the PI controller. Yeah. Everything is already running on Python, so I can just start coding. And kind of like I mentioned before, when I was doing the derivation, we kind of already explained the last part. Oh, whoa, 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 whoa. What the heck? Why am I? What the heck? I don't know what that was, but let's keep going. Let's copy paste ourselves. Um, but kind of like I was about to say. Kind of what we did in the derivation. What I explained on part A. Um, for the second part where the second order, the first order is for a time delay. I mean, if you remember our, actually, let me just pull this up. Actually, no, I can explain it. But if you remember our derivation that we did for a time delay, we know that for the time delay portion, the domain range is from 0 to negative infinity. And we know once we know just for any controller, once we have our, what is it? Once our amplitude, our, no amplitude ratio, but our phase lag goes past negative 180, then from that point on, we know that our controller will be unstable. So we know with a time delay, we don't really know how we can. For a time delay, there will be a point in time where the system will become unstable. So even for first order or second order, if we put a time delay in, we cannot guarantee stability. So over the amount of time, a lot amount of time, our system will be unstable. Whereas for the PI controller, the one where it is derived, um, this would not happen. Because we know our range can only go from 0 to negative 90. So it never even reaches negative on 180 degrees. So, and I'll show this right now. So let me pull up, no, not this. We need that for the next part. Pull up the paper, trusty old paper. Um, you know, this is fine, this is fine. Let's bring the tau back to 1. That was from up here. Theta, yeah, we need a tau I now. So I have to get a tau I in here. Let's say that's equal to 1. Then for our IR amplitude ratio, let's put our three transfer functions. So our GC, our GP, and our GM. Yeah, we know our DM's equal to 1. Our GP for process, we know that's equal to K of tau times, and we're using, this would not be in the Laplace domain, it'd be outside Laplace domain, so we do uh omega times uh 1J. When you use a capital K. And then for our DC, we know that will just be KC times 1 plus 1 divided by tau I times omega times 1J. And again, we know why reason why we're using 1J instead of just using J for imaginary numbers because Python's not like us not having a coefficient with our imaginary number. So we need to have a coefficient. So we put 1J. Okay, so from here we got to take all this out. You know our IR is equal to GC times GP times G. Okay. Everything else will stay the same. This will be figure 5. And everything should work now. So we should enter, should enter. Interesting. I think I deleted one. Let me see. Yeah, I deleted an entire section. Okay. Like we only have our phase left. I mean, actually, this is what does it even apply to? Okay. Let me space out the range. So range is equal to, let's do what? Negative 270. Sorry. Mine went to a blank. 2 0. And then let me increase this to 3. It's not getting the entire slope. Um, okay. That's not what I want it to look like. Do you need data? We do not need data, but that's fine. Oh, we have KCK. Um, we have our KC. Let's put our KCs 2. Let's put the KC to 1. Let's put everything into 1. I don't know why it's not doing what I want. Oh, this is frustrating. Okay. Um, I'll be right back. Let me check what the problem is. Yeah, this is a small mistake. I forgot to put the +1 for the GB printer. Oh my gosh, I just studied like crazy for the GP transfer function. So now I just add +1, and we should enter this now. Let me shake it. Oh wow. Oh, I think it's because our tau I is 1. Let's put this at 0.1. Yeah, we go. All right. So here is what our PI controller will look like. Go back to the prompt. This is what our PI controller will look like. And as you see, here we go. This is our phase lag. It's on the top. No, this is no M2 ratio is on top. Here's our phase lag. And as you see, we don't even get close, and we get close to negative 180, but in every region, negative 180, how does a little slope up, little dent, and it comes back up. So we know this will always be stable. As you look, this will all be stable. And even if you change, the tau I, if we go to, let's see, if we make omega bigger, let's say this is 5. We get closer, but it doesn't really change. And we can also change the tau I. So we make our tau I, it's bigger. We do just 0.1 instead of 0.01. Um, Oh, I meant one. I accidentally put zero for tau I. But yeah, as you see, either any way we would adjust our our controller or from our tau to our omega, it will never reach negative 180. It will get close for sure, especially if you make the tau I extremely small. It will probably get really close. So let's we do it to this very significant power of tau I. Like you see, it's so close to getting negative 180, but it doesn't. It comes right back up. So it's impossible for our controller to be unstable. It would always adjust based on the errors that it shoots out and make it so it will stable out over time. Okay. Last two is we compare it to the first order and second order system if we incorporate a time delay. Let me change this from this is with PI first order PI controller. First order controller. Let's see if we look at the first order time transfer function with the time delay, like we did with our first part A, we see that at a given amount of time that we will once it reaches negative 80, 180, it will become unstable over time. So if you add incorporate time delay with our first or second order functioning system, it will become unstable over time. Whereas if you do a PI controller, it will never become unstable. Even if you adjust the controller to like try to make it fail, it will always not fail if you don't use a time delay. Okay. So that's the first part. Now the second part, and I figured out what the FOPTD meant. Our second part is that they want us, we were asked to graph out a first order proportional integral proportional integral time delay system. So we're incorporating the PI controller and also a time delay into a system. We put we're given a certain amount of prompts for our KC and our tau and our time delay, and we are asked to make it as optimal as possible using the integral time weight absolute error. Okay, so this is well. First, we're supposed to just create uh, this model and also incorporate this with a Bode diagram and see how it will try to make it as optimal as possible to make it as less try to have it as so it does not oscillate over time. So make it so the system doesn't oscillate and become stable the fastest amount of time as possible. So make it most optimal. And then after that, we incorporate this integral time weight absolute error, which is this bad boy right here. This is the equation based on numerous amount of experiments scientists did to basically figure out what would be the most efficient time that you can set your PI controller to be. Okay, so scientists did multiple experiments and runs, figuring out what are the best ways to find our basically our tau and our K values for our PI controller, for our PI and PID controllers. Um, and we are using these set numbers right here. And the equations right here for the y is equal to A times tau theta divided by tau B, and then the y is equal to K times KC. This is how we'll find our K value, our KC value, our gain in this case. And then for the second part, we will use the divided by tau I is equal to A plus B times theta divided by tau to find our tau I. Okay. So we'll use the given prompts from the graph to then basically figure out what's the two differences from what we have the modeled out, the most optimal, and then what scientists have found overall. Okay. So that's the next step we'll do. So let's start with that. We'll just start here. Of course, I'm going to copy and paste everything. But we will not be using some stuff. Um, And I'll also make a bidet diagram. And we have a bidet diagram from earlier. I'm just going to copy and paste. Can I use this one? Oh, I can. Perfect. Um, sure, I'm just going to, so they're all in the same section. Oh no, my bad. Oh, it's a what isn't there? We don't need this. We just need one for time. Okay. All right. Let's get started. Um, we will be need to be in the Laplace domain for this. So let's FO P PD model. We're not using omega because we will be in the Laplace domain because we're just using S. And we will not be using KC because we'll be using the equations or tau I. Okay. And I'll put a code up here. We need to take the set points. So the 0 point, we'll do PA and PB for our PI model. And for set points, we will have, what is it, 0.5, A6, and negative 0.916. And then for the I integral, we will have, we'll do IA, IB, and then we'll do 1.03, negative 0.165. Okay. Now let's do the equations. So let's start with y for the top part so far. Can I zoom in? I can. Perfect. So we do our A section first, so the y. So we know that y is equal to A of theta divided by tau to the exponent of b. And we have that labeled as PA and PB. So I'll put the P in front of the PA and P and the A and B. Okay. And we know that we're trying to find KC. So KC is just equal to Y divided by K. Okay. So now we have our KC from this, and then we want to find our tau I as well. So we know that, to find that, we know that tau I is equal to A plus B times theta divided by tau. Well, there's no exponent here. And then we would need to divide this by theta, and it has to be its inverse. So it'd be 1 over 1 divided by, it'd be, well, first I'll put the i's here to get our numbers. And then it'll be 1 divided by, this ti's in the numerator, denominator. We need to put this in the numerator. So it'll be, actually, no, all of this be, this would be tau divided by this would be tau divided by IA plus IB times theta divided by tau. Okay. We can actually move all this into this section here. So we can do it right below here. Oh no, I did it again. Actually, just copy and paste again. All right, there we go. Now we have this section here. So now we have our KC and our tau I. To replace, excuse me. Okay. And now we just have to change our DC, GP, and GM. So our we have to change our Hammett functions because they're also outside of the Laplace domain because we plugged in our omega and our J. So we just have to delete these and put S here. And of course, remember we have S up here from our earlier library. So it's fine if we use this. So S, this will be S. Okay. I think we're good. In the last part, I remember we had to do something different. Um, to pull out our empty ratio and our phase, we have to we have to do something different. Um, it's blanking right now. It's blanking right now. We don't have to actually do this part right now. I'm pretty sure. Let me just check. I'm gonna just do it like this, and then this doesn't work. I'm gonna check the other way, and then we also have to. And the last part we have to oh, for the bodega diagram as well. We have to change this as well, so we can delete this. And we already have the transfer functions up here, so we can just do the overall transfer function for the system. So FP, this is be GC times GP divided by 1 plus GC times GP times GM. Output's in the bracket. Oh, let's do case P. Put it in a bracket. Okay. And then let me change the figure numbers. Fix 6. I wish there was a faster way. I mean, there is a faster way. I'll be watching Jay videos, and he always says it's a faster way. But I just don't know the faster way to change them all simultaneously. So we're just going to do it one by one. And fix 7. All right, so hopefully this works. We can test this out. Shift enter. Float is not callable. What's not callable? Oh, probably multiplication sign. There we go. Should work now. Integer arctan. That's why, because now we can't use arctana 2 now. Using the doing this way. So we have to use a different method. So yes, this will not work. I knew there was a problem with doing this method. Okay, so let me get these out the way. I'm not sh really sure how we do the other way. I'm not even gonna try to fake it. So I will be right back. Um, and I can try to see kind of explain this. We'll see. Um, oh, hold on. I've totally skipped a step. Um, I totally skipped a step. This is the last part. We're supposed to be actually using the given information, so I'm gonna copy this. Um, yeah, this is for if we use when we use the IT at the integral time wait absolute error. I totally skipped it. We're supposed to use the given information first. Um, I'm gonna label that as well. I mean it's the same code. It is one uses one is using given numbers, one does not use given. So it's kind of different. Um, I want to do what data for this one as well. Okay. Um, this is no ITA model. So we don't actually need none of this information right here because we were giving it. We were given it. Okay. We know that our KC is equal to 1. We know our game's equal to 1. We know that our data is 0.1. We know that our tau is also 1. Okay. Actually, no. This can be 0.1. But we know that our time constant, which is our tau, is 1. So we know our Kc is 1, our tau is 1. Okay. And we say our tau is just 0.1. Where's that's the part we're trying to optimize. Yeah, we still have to figure out the one other method for plotting this. So I'll be right back. And this should be my last pause. And then also from this, I can update both of these graphs as well. Okay. So I'll be right back. Okay, so we actually don't need none of this. Okay, we can get rid of that actually. Let me combine these. Merge, merge selected cells, and then the last part. We gotta add this line right here. What is it called? And then AR, and then our phase. This is equal to bow day. And we're gonna do our DC times our GP times our GM, and then our omega. We're still pulling our omega term. Okay. Shift enter. Interesting. Um, Interesting. Why is it still having? Oh, because I forgot to add the time delay. Yeah, I forgot to add the time delay. So we have to also incorporate the time delay. I totally forgot about that. So that would just be um plus. I was like, why does it look like this? It shouldn't. Okay, and time delay is right. Where's it at? There's a lot going on. Let me see if this is the right settings. Wi-Fi model. This is our PI controller. Okay. But then the time delay should be right here. Where's it at? There we go. Yeah. So it'll be for, you can add it for our controller. Yeah. So for the controller, it'll be, I need for a process. For the time delay for a process, it'll be plus, um, actually be times, and then we use XP, which is just exponential. We don't have to state that. And we don't have to use NP because we already stated it in the libraries as well. And this would just be theta, negative theta, times S. I'm thinking sure that's correct. Let me check. That's the transfer function. Time delay. There we go. Yep, should be right. Let's add it to the wrong column. Oh my gosh. Okay, there we go. Okay, let's try this now. Yes. Okay, we have it now. Let me see if it's supposed to be plus. Let's change this to plus and see what's the difference. No, but yeah, it's definitely times. It's definitely multiplication. Yeah, it's definitely times. It's definitely time variant. Okay. And I had the same issue. Like my ranges for the are extremely high. I don't know why that's the case, but I know it's terrible. Um, let's change the DTIC to 30. Let's do Yeah, let's just do 30. See, that helps with that helps more. Okay. Um, and then for this part, we need to simplify the GFP. So we do GFP equal to simplify, and then GFP. And now this should work. And we change whatever function here is FB. Okay. All right, perfect. And then we can space this out. Super zoomed in. Um, yeah. So this is what. Okay. So let's kind of explain this. So this is our now our PR controller. Using me our yeah first order transfer function, first order PI controller. Using the our time delay function. This is correct. I was trying to I was working on this earlier and my x-axis is very large and I wanted to be deduced, but I really just don't know how to do that. But we can explain it still and kind of yeah, we can just zoom in. But like we have it here, we start at -90. We have our first layer of time delay before we will see kind of where our time delay starts. I mean where our first order exponential starts. And as you see, we have when we have -180, it's 8.23. So we can try to go here, 8.23. Roughly around here. It's below one. So this function is stable. And as you see, we do have a stability. So this is showing our stability of our controller. Um, it is stable. But we do see there's a kind of a spike, a little oscillation before we reach one, where it stables out at one. Um, and we can try to make this more optimal. We can change our controller to see what that does for us. How is this saying? Let's maybe let's try to change our tau like 0.5. The goal is not to have that spike. Yeah, you see how it kind of levels off a little bit now. It's more stable. It still takes a little bit while before it reaches one around like 3 point what? Around like 2 seconds. So it takes 2 seconds. It's not kind of simultaneous instantly. Um, but it does stable out. Let's try one. So if our tau I is one, oh perfect. Yeah, perfect. Okay. So when our tau I is one, perfect. It will become more optimal. I kind of already know the answer. I'll just, try to drag it on. But it's because when we do this, we will have 1 divided by 1 times s. So 1 plus 1 divided by 1 times s. So it'll just be 1. So our whole system, it'll just come up to 1. So there's no, so nothing divide, the numerator, the denominator would be 1 divided by, so it'll be 1 divided by 1. So 1 would be the kind of the most optimal, um, way. I mean, make the PI controller make the system most optimal when tau is equal to 1. So yeah, this is what our system will look like. Yeah, I'm sorry for it being kind of zoomed out. I was trying to fix this earlier in the day. It didn't work either, but now you see like there's no really time delay anymore. We kind of see it first, we just see like the exponential function happening. So with this model, we kind of don't have a time delay anymore. It's kind of just a straight line before we start reaching our time delay. But yeah, here it is on the most optimal version of our FOPTD model. Okay, so now we'll move on to the model using the given numbers and using the equations from the R integral of time-weighted absolute error equation. Okay, I'll be right back though because my Zoom recording is about to die. I mean, about to end. So I'll be right back with the rest of it in about like 10 minutes. You won't be waiting 10 minutes, but I will be waiting 10 minutes. Okay, I'm back. My long-awaited break for the Zoom. Um, where were we? Um, yeah, okay. So we just plotted out the FOPD model, just using the closed loop system, not incorporating the ITAE equations yet. Yeah. Okay. And then we found the optimal PI controller gain by adjusting our tau I to just being 1. And I think let's see if we change our controller. So let's take this back to 1. See what that does. I mean, it doesn't. Yeah, I think our optimal is just changing our TI to 1. It kind of makes sure there's no time delay anymore. So now it goes back to a regular. Um, well, it doesn't not deal with time delay, but it makes it so that is very doesn't really change the stability. So our stability goes the fastest when our tau I is 1. Okay. So roughly around what? Like 1.9 seconds. It says 3.6 to 1, but it was 1.99 for a longest. So we're going to say, I mean, no, it was like 3.6 when it's 1. But we are trying to make it as fast as possible. So using this ITAE, this um, model should have us have make it so that our controller can be as fastest and most optimal as possible using the scientists who ran this experiment multiple times. So now let's do this. I already have the parameters because I actually kind of got ahead of myself. Um I'm gonna copy and paste everything we have up here. Let me just put this to 9 now. Now let's put this to 8. Not change the order. Yep, 8. And we're gonna fig. Oh no. There you go. Oh no. Okay. There we go. Oh my gosh. Oh, almost there. The last one. Okay. Um, Let me add this bad boy right here. And then let me just combine these as well. Oh, I don't need this. I just hide this. There. And then merge cells. And then paste this. Now I should enter. Well, that's wrong. That's totally wrong. That's wrong. Let's see. Oh, okay. Well, it's not wrong. Yeah. So basically, the super zoomed out version. Um, I don't know why that's on the y-axis. Let's see. It's not showing the y-axis, which kind of sucks. Um, y-axis goes to okay, and then oh, it's super zoomed in. You zoomed out. That's why. Yeah, this is the zoomed in. Okay. So yeah, basically, um, as you see, this is our controller. And when does it get to 1? So yeah, this is the controller using our ITAE. Um, and you can kind of see that it goes extremely fast. We actually reached 1 at 1.2 seconds. Around near 1.2 seconds, which is cuts 2 seconds from what we just had using our other controller. It took us around 3.2 seconds to get to 3.6 seconds to get to 1 with no oscillations. So yeah, this is much faster, much more efficient, way faster. And I know the scale kind of looks off, but this is basically saying the lowest it can go from the given numbers is literally to only -91. It's not even close to -80, so it's definitely not gonna be unstable. This is extremely stable. Um, yeah, so this is what we kind of have here. I can't even get the -180. Like right here, what is it? It's 0.96. You go to 0.96. I think I was really just hovered over it. Let me zoom in. At 0.96, our empty ratio roughly around, oh, it's around 5 though. That's not right. Why is our empty ratio so high? Um, it shouldn't be, it should be lower than 1. At 0.96, it's that high? Interesting. Hmm. It's stable. It's extremely stable. So that's you got that. I'm just kind of confused. We kind of don't have to worry about AR because it's not even close to one. We don't have to worry about the empty ratio because it's not even close to negative 180. It still should be under 1. It's kind of confusing. I don't know. Kind of confused. Should be neg It should be under 1. I don't know why it's not under 1. Hmm. Not sure. Let me adjust my. It's because the tau. Let's adjust the tau to 5. See what that does. Maybe get the auto scale it again. Um, what is that? 0.2. I think our tau has to be smaller. Let's try 0.5. Oh, there we go. Let me see. We have it to what? 2.11. It's getting smaller. Let me also do my K value. Oh, my bad. Auto scale. 1.92. Hmm. Okay. Well, with this though, you see that our see even if we change this, I think it's still very yes, it got faster. So it got faster. So as you see, this is the most optimal. We do have to change our K and our gain and our time constants to adjust to our A and one adjust to our AR being under 1. Even though our empty ratio wouldn't have to be a factor because um it's not even going to be close to ever reaching negative 80 degrees. Um, but yeah, this is our model for our first order uh proportional integral transfer time delay model um for our system. This is the most optimal version using the scientific method, the integral time weight absolute error method. Um, yeah. I think that's it. Let me answer all the questions. We did do the sign. We did the Bode diagram showing the calculated parameters with the closed loop section. This would be the closed loop. We saw changing the variables, adjusted with the helped fluctuate the time steps. So that answered that question as well. And kind of we did kind of a little bit with this, but it didn't really change anything. I think it was already. I think it's now just yeah. I didn't really change anything. This we did do the time steps for the top as well. So we did do the closed loop by the diagram, and then do the time step changes as well to see how it affected our Bode diagram. Okay, that's it, ladies and gents. This is the last video. Process dynamics and controls. It's been a long journey. Yeah, I will see you guys later. You can check out my other video. For separations, which will be also on my channel. But yeah, I will see you guys later. See you.